In 2019, a quantum processor finished a calculation in 200 seconds that would take a classical supercomputer 10,000 years to verify. That gap is not just a speed difference. It is the beginning of a place where we lose the ability to check if the answer is even correct. The question this raises is not whether quantum computers are fast, but whether they are reaching a zone where classical physics cannot audit what they are doing. By the end of this video, you will understand what happens when a machine works, but we cannot prove why it worked, and what that breakdown says about the limits of verification itself. The core tension is simple. A classical computer runs on bits that are either 0 or 1. You can always retrace the logic step by step and confirm the answer. A quantum computer runs on qubits that hold 0 and 1 at the same time until measured. The calculation happens through interference, where wrong answers cancel out like waves and the correct solution survives. That process is not something you can pause and inspect.
The moment you try to look inside, the quantum state collapses and the calculation vanishes.
So the first question is whether you can trust a result you cannot watch being built. Here is the first concrete trace. To perfectly simulate a 100-qubit quantum computer, you would need a classical hard drive larger than the number of atoms in the visible universe. That is not an engineering limit. It is a mathematical wall. Classical simulation works by tracking every possible state the qubits could be in, and the number of states doubles with every qubit you add. At 100 qubits, the state space explodes past what any classical machine can hold in memory. The old model says that if a computer produces an answer, you should be able to verify it with a smaller, simpler machine. But here, the verification machine would need to be impossibly large. The mismatch is not about speed. It is about whether verification is even possible in principle. What this changes is the assumption that every calculation leaves a classical audit trail. The second trace comes from the environment these machines require. Quantum processors operate inside dilution refrigerators at 15 millikelvin, a temperature significantly colder than the vacuum of interstellar space. At room temperature, thermal noise would destroy the quantum state in microseconds. Cooling the system that far is not just about stability. It is about isolating the qubits from the classical world long enough for interference to happen. The old model treats computation as a process that can happen anywhere, as long as the logic is correct. But quantum computation only works when the system is almost completely disconnected from its surroundings. The contradiction is that the machine must be shielded from reality in order to produce a result we can use in reality. What this reveals is that the quantum calculation is not robust. It is fragile, and that fragility is built into the physics. The third trace is the task itself. The 2019 result used something called random circuit sampling. The quantum chip runs a series of random quantum gates and produces a pattern of outputs. Checking whether that pattern is correct requires a classical computer to simulate the same gates and compare the results. For small systems, classical machines can keep up.
But as the number of qubits increases, the classical simulation time grows exponentially. At 53 qubits, the classical estimate jumped to 10,000 years. The old model says a faster machine should not change the nature of the problem. But here, the quantum machine crossed a threshold where the classical machine cannot finish the verification in any reasonable time. The result is that we are forced to trust statistical tests instead of direct confirmation.
The quantum computer produces a distribution of answers, and we check whether that distribution has the right shape. We are no longer checking the math, we are checking the fingerprint. What this changes is the definition of proof. The fourth trace is the no cloning theorem. Fundamental physics forbids making an exact copy of an unknown quantum state. In a classical computer, you can copy any intermediate result and inspect it without disturbing the calculation. In a quantum computer, copying a state would require measuring it, and measurement collapses the state into a single classical value. That means you cannot duplicate the quantum work and send one copy to a verification machine. The old model assumes you can always snapshot a process and check it later.
But quantum mechanics does not allow snapshots.
The contradiction is that the thing you want to verify is also the thing you are not allowed to copy. What this forces is a shift from replication-based proof to interaction-based proof, where a classical computer asks the quantum computer questions and tries to catch it in a lie, without ever seeing the internal state. The fifth trace comes from error correction. Quantum states are so fragile that it may take 1,000 to 10,000 physical qubits just to create one stable, error-corrected logical qubit. Engineers are now maintaining quantum coherence for durations previously thought physically impossible by using error correction to fix states before they collapse. The old model says that if a system is unstable, you cannot build anything reliable on top of it. But quantum error correction works by encoding one logical qubit across many physical qubits and constantly measuring for errors without measuring the logical state itself. The contradiction is that you are observing the system to protect it, but not observing it enough to collapse it.
The error correction is succeeding,
but the fact that it requires 1,000-to-1 overhead reveals how far quantum computation is from the classical ideal of a single, stable bit. What this changes is the cost of trust. Every logical qubit you want to use reliably costs you 1,000 qubits you cannot use for anything else. The sixth trace is the verification blind spot. We are reaching a point where no classical computer exists to double-check if a quantum answer is correct. The only way to verify a quantum result may be to build a second, more powerful quantum computer to check it. The old model treats verification as something you do with a simpler tool than the one that produced the answer. But if verification requires an even larger quantum machine, then trust becomes circular. You are trusting one quantum computer by asking another quantum computer if it agrees. The contradiction is that verification was supposed to be independent, but now it is entangled with the same physics it is trying to confirm. What this reveals is that we are moving toward a future where the only proof is consensus between quantum machines, not reduction to classical logic.
The seventh trace is the complexity theory argument. We trust quantum outputs not because we can redo them, but because faking the answer would require breaking fundamental laws of computational complexity. If a classical computer could fake a quantum result quickly, it would mean that entire classes of problems we believe are hard are actually easy, and that would overturn decades of complexity theory. The old model says you prove correctness by checking the work. But here, you prove correctness by assuming that lying is harder than telling the truth. The contradiction is that the proof is not in the answer. It is in the assumption that no shortcut exists. What this changes is the foundation of trust. You are no longer trusting the machine because you checked it. You are trusting it because you believe the universe does not allow a faster fraud.
The eighth trace is direct simulation of nature. Quantum computers do not just calculate molecules. They act as the molecules, simulating chemical bonds that classical math can only approximate. A quantum processor running a molecule simulation is not translating the physics into binary. It is instantiating the same quantum rules the molecule follows. The old model says simulation is separate from the thing being simulated. But in quantum computing, the simulation is physically identical to the target system. The contradiction is that the line between model and reality dissolves. What this changes is the meaning of computation. The machine is not representing the answer. It is becoming the answer. The ninth trace is the measurement collapse problem. The moment a human or a sensor observes a calculation, the infinite possibilities vanish into a single, mundane, classical result. Every quantum algorithm ends with a measurement that destroys the quantum state and leaves behind a classical number. The old model assumes you can watch a process unfold and understand it, but quantum mechanics forbids observation during the process. You can only see the input and the output. The middle is invisible. The contradiction is that the computation happens in a space you are not allowed to enter. What this forces is a change in how we think about understanding. You cannot understand by watching. You can only understand by inferring from the result. So here's the answer to the title question. Quantum computers are reaching answers classical physics cannot audit because verification requires simulating the quantum process, and simulation requires resources that exceed the physical limits of classical storage and time. The evidence eliminates the idea that every computation must leave a checkable trail. The result still has no full account for what the quantum computer is physically using when it produces the answer. Physicists still disagree about whether the machine is exploring parallel branches, exploiting hidden dimensions of state space, or simply following quantum rules we do not yet see as intuitive. The mechanism is strongest in the interference model, where wrong answers cancel and correct answers survive. But the interpretation remains open. What is still unresolved is whether working quantum computers will force a consensus on the meaning of quantum mechanics, or whether they will remain black boxes that work without telling us why. What this changes for you is the assumption that science always moves toward more transparency. Quantum computing is moving toward a place where the answer is real, the machine is real, but the explanation is still contested. The result works. The audit does not. And that gap is not a bug. It is written into the physics. If you want to see where the edge of verification lives, you are watching it form right now.